Hello there, I'm Fahmi. I'm a mechanical engineering student at the University of New South Wales. At the end of this video, you should master about these topics, which are linear and angular momentum and mass moment of inertia. The kinetics of rigid bodies treats the relationships between the external forces acting on the body and the corresponding translational and rotational motions of the body. In addition to the two force equations of motion for planar motion of particles, an additional equation is needed to specify the state of rotation for the plane motion of a rigid body. Thus, two force equations and one moment equation or their equivalent are required to determine the state of rigid body plane motion. General equations of motion. Generally, for a rigid body in 3 dimensions, sum of forces equal to ma, where sum of F is the sum of the external forces acting on the body, m mass of the body, and a acceleration of the center of mass g. The equation of moment at the mass center g is the sum of moment equal to h dot, where sum of m is the resultant moment about the mass center g, h dot is the rate of change of angular momentum about the mass center g. By replacing the external forces by their equivalent force-coupled system in which the resultant force acts through the mass center g, we may visualize the action of the forces and the corresponding dynamic response of the body. Part A of the figure shows the relevant free body diagram. Part B of the figure shows the equivalent force-coupled system with the resultant force applied through G. Part C of the figure is a kinetic diagram, which represents the dynamic effects as specified by the force and moment equations. The equivalence between the free body diagram and the kinetic diagram enables us to clearly visualize and easily remember the separate translational and rotational effects of the forces applied to a rigid body. Plane motion equations. The figure represents a rigid body moving with plane motion in the xy plane. The mass center g has an acceleration a and the body has an angular velocity omega and an angular acceleration alpha, both in counterclockwise direction. Since omega and alpha are perpendicular to the plane of motion, the scalar notation omega and alpha equals to omega dot may be used to represent the angular velocity and the angular acceleration. The angular momentum about the mass center for a general system is given as, where ρi is the position vector relative to g of the representative particle of mass mi. For our rigid body, the velocity of mi relative to g is ρi dot equals to omega rho dot, which has a magnitude ri omega and lies in the plane of motion normal to ρi. Thus, the magnitude of hg becomes the summation ρi squared mi, which may also be written as integral of rho squared dm, is defined as the mass moment of inertia of the body about the z-axis through g. We may now write hg is equal to I bar omega. With this substitution, the moment equation becomes the sum of moment is equal to I bar alpha. If we choose some arbitrary point P, in the planar case, this reduces to MP is equal to I bar alpha plus M A bar D, where D is the distance from P to G in the direction perpendicular to A. If we want to write the equation in terms of P, MP is equal to IP alpha plus RG respect to P times MAP. If there is some fixed point O, then MO is equal to IO alpha. Mass moment of inertia. Moment of inertia is a measure of how the mass of an object is distributed about its axis of rotation. Mass moment of inertia about the axis OO is I is equal to integral of R squared dm. The moment of inertia integral may be expressed alternatively as I is equal to summation of Ri squared times Mi. The dimension of I is kilogram meter squared. The radius of gyration k of mass m about an axis for which the moment of inertia is I is defined as k is equal to square root of I divided by m, or I is equal to k squared m, where I is the moment of inertia and m is the mass that concentrated at a distance k from its axis of rotation. The object is rotating about the fixed spin at O. The parallel axis theorem is IO equal to IG plus MD squared, where IO is the moment of inertia of the object rotating at O, IG is the moment of inertia of the object rotating about its center of mass G, M is the total mass of the object, and D is the distance between the two axes of rotation of O and G. Note that axis of rotation of O and G must be parallel. As an example, let's try to answer this question. The 300 kg concrete block is elevated by the hoisting mechanism as shown. The drums, which are fastened together and turned as a single unit about their mass center at O, have a combined mass of 150 kg and a radius of gyration k about O of 450 mm. If a constant tension P of 1.8 kN is maintained by the power unit at A, determine the vertical acceleration of the block and the resultant force on the bearing at O. The free body and kinetic diagrams of the drums and concrete block are drawn showing all forces which act, including the components OX and OY of the bearing reaction. The resultant of the force on the drums for centroidal rotation is the couple I bar alpha is equal to I naught alpha. Taking moments about the mass center O for the pulley in the sense of the angular acceleration alpha gives equation 1. The acceleration of the block is described by, and this is equation 2. You know that tangential acceleration is equal to R alpha, and we get that A is equal to 0.3 alpha, and that is equation 3. Solving equations 1, 2, and 3 simultaneously, we will get that T is equal to 3250 Newton, alpha is equal to 3.44 radian per second squared, and A is equal to 1.031 meter per second squared. To find the reaction forces, use the equilibrium equation. Sum of force in the x direction is equal to 0, and we will get that OX is equal to 1273 Newton. In the y direction, the sum of force is equal to 0, and we will get that OY is equal to 6000 Newton. After we got these two force components, we can find the resultant force on the bearing at O. Therefore, O is equal to 6130 Newton. Alternatively, we may use a more condensed approach by drawing the free body diagram of the entire system, thus eliminating reference to T, which becomes internal to the new system. From the kinetic diagram for this system, we see that the moment sum about O must equal to the resultant couple I bar alpha for the drums, plus the moment of the resultant MA for the block. Thus, Sum of moment at O is equal to I bar alpha plus MA bar D. Previously, we got that A is equal to 1.031 meter per second squared. We may equate the force sums on the entire system to the sums of the resultants. Thus, we'll get that OY is equal to 6000 Newton and OX is equal to 1273 Newton. Using these two forces, we'll get that O is equal to 6130 Newton. We can see that the answer is the same as the previous method. Okay, that's the end of the lesson for today. I hope that this video may help you much about this topic. Last but not least, wish all the best in this subject. Thank you. Bye.